that's a short announcement. And now let's see what we have in section 3.4. That's what we will be looking. We will be looking at limits at infinity, or using different words is we will be checking how function behaves at infinity, like the end behavior. Because limits at infinity, as x becomes like arbitrarily large in the positive or negative direction, we will be checking how the values of the function behaves. Are they also like approaching infinity, or maybe negative infinity, or maybe they are, let's say function is increasing and they're not gonna be greater than a certain line, certain horizontal line, which of course we call horizontal asymptote. But let's see. That's what we did. We did something like that. I can show you this. That means in chapter 1, we were looking at infinite limits. But this is a little bit different, because this means that the limit at the number as x approach the number, and most likely is the number that is not in the domain. Yes, we can see limit number 1, x approaches 1 from the left, the second one is 1 from the right hand side, but 1 is not in the domain. That means if the number is not in the domain, we have to check how function behaves close to that number on the left and on the right hand side. That's when we computing a limit. That means having this 3 minus x over 1 minus x, substituting 1, I'm getting 2 over 0. But of course, this is not really 0, because this was not really 1. 1 from the left is like 0.9. 1 minus 0.9 is giving me positive number, positive tiny number. Of course, I write 0, but it's just tiny number. And a number over small number, and this one it's a big number. That's what I was gonna say. This one will be 1.1, 1 minus 1.1 is a tiny number, 0, but it's negative. Then we have negative infinity. Okay, and this one, of course, the conclusion is, if we getting a limit, if we getting an infinite limits, the outcome, the conclusion is that that line that wasn't in the domain and the limit was at this point, this line is a vertical asymptote. And I don't want to draw an entire function, but I can only do the line 1, x and y, and how function behaves. On the left-hand side, function is going up. On the right-hand side, function is going down. Okay, that's just to know. And of course, we will not investigate the whole function. Okay, that was the old stuff. Please note, because the summary in section 5 will be, one of the questions will be find a vertical asymptote. That means find the numbers that are not in the domain and compute a limit. If the limit is infinity, this line is a vertical asymptote. If this limit is a finite number, then it's not, then it's probably like a hole. We remember types of discontinuity will be simply like a removable discontinuity, not the infinite. Okay, that means now let's look at the end behavior, like how function behaves as x becomes big in the positive and negative direction. And what I have a function, 1 over x. X, of course, 0 is not in the domain, probably is the easiest rational function. And I have this settings. I type this for you. Okay, that means the top is still the old stuff. I will change my color. It's the old stuff, is the investigating how function behaves at 0 from the left and from the right-hand side. Oh, one of them should be right. Because 0 is not in the domain. And we probably remember 1 over small number is a big number. That means this is infinity. 1 over small number is a big number, but it was small negatives, negative infinity. And this will be the conclusion. 0 is a vertical asymptote. Okay, now let's check how this function behaves at infinity. What's happened if x is extremely big? And I do have a graph, okay? And we can see if function, oh, hang on, because I have this. Okay, function is approaching, like, I mean x is getting bigger and bigger, the whole values are getting smaller and smaller. Okay, oh, my writing is, I'm trying not to lean against my laptop because then we're losing voice. Okay, that's we can see this behavior, like 1 over x, 1 over 1, 1 over 2, 1 over 3, 1 over big number is a small number. Yes, we remember also this, like from the basic arithmetic. 1 over big is small. Okay. 1 over big is just a small number, which is worth to remember. Of course, big for us will be infinity. 1 over infinity is 0. That means I can put 0 and 0. And for this one, we don't even have to distinguish the difference. Is, of course, the top one is approaching 0 from, I mean, the positive infinity is approaching 0 from the top. Negative infinity is approaching 0 from like the bottom. But 0 is 0. We don't have positive 0 or negative 0. Okay, and now the important thing for this section is the conclusion. Limit at infinity. If the limit at infinity is a finite number, this finite number is a horizontal asymptote. Horizontal asymptote. Okay, that's the main thing. And I have just the definition, which probably we okay with this. It's just the notation, but it's exactly the same like in chapter 1, like where I introduced the limits. That means let f be a function defined on some interval from number like a to infinity. Then the behavior of the function at infinity is L. This means that the value of f of x can be made arbitrarily close to L by taking x sufficiently large. Of course, L will be the horizontal asymptote, that the value of the function are approaching L. Like we know, we're saying we're really using an equal sign, but we know the meaning of the limits. Let me just come back. We can see the blue curve is not touching 0, but the limit is 0. The function will be not like higher or lower than 0. Okay, and we can have the situation on the negative or positive infinity, the same thing. Okay, and we can read, like we have different like ways to express this. The limit of f of x as x approaches infinity is L. The limit of f of x as x becomes infinity is L. Like any way is good. The understanding is important. Okay, and then just the conclusion by using these symbols. If the limit at infinity is L, we will call this horizontal asymptote. This line y equals to L. It's a horizontal asymptote if that limit is a finite number L. Okay, that's what we will do. Oh, okay, I have just a few graphs. Oh, actually, the graphs are important because let's see something. We always have this feeling that asymptote is the line that we can't touch. And this is correct. But we have to always remember where we are. Like, since we're looking at the limits at infinity, okay, a function like as xx is getting bigger and bigger, as x is arbitrarily large, then this is the horizontal asymptote. Then the function can't touch it. That means horizontal asymptote, we have to respect horizontal asymptote at infinities. Something like in the middle, like you can see, we can simply intersect. That's not a problem. Like, which example is good? Let's say this one. Yes, this one is like, we can see one intersection, another intersection, but at negative infinity, the blue curve is definitely respecting an asymptote. Okay? It's definitely like we will not touch. The function will not touch. I can remove my red, not touch the line. This one is fine. Probably this limit was only at negative infinity. Let's look at this graph. This graph actually has different asymptote at negative infinity and different and positive infinity. Just in case, if you will have, I don't know, true and false question or any question related to horizontal asymptote, what is the maximum number of horizontal asymptotes? What do you think? For the given function, what will be the maximum horizontal asymptote? It's 2. Thank you very much, Robert. Thank you. Because we may only have the difference between negative infinity and positive infinity. We may have the same, no problem, but we may have different behavior. That means 2. We can't really have 3 lines, I mean, or even more than 2, more than 3. No, 2 is the maximum. And now, of course, I really want to ask you this question. What is the maximum number of, if any, of the vertical asymptotes? Do you think function will have some limitation? Can we have, no, thank you, Pete, thank you. That means no, not, yes, of course. We may have infinitely many, depends. I may have, especially for the rational function, I may have a function from the denominator, like let's say degree 10, I can find all of the zeros, and all of the zeros, if the limit will be infinity, infinity, oh, really nice symbol. I don't know how you type this, Robert, but yes, we may have infinitely many asymptotes, because all of the zeros from the denominator may give me a vertical asymptote, vertical line. Okay. That means that's the case. Look, let's look at also this one. This one is interesting. We kind of like intersecting like infinitely many times. And this one you can probably say, oh, you just said that we can't intersect at infinity. I know this is probably some trigonometric functions involved. We kind of like we intersecting, but still function is approaching. We can see this kind of like a snake. It's definitely like oscillating between that line, and this line will be definitely an asymptote. And I don't have the formula for this example, for formula of the function, but having a formula and computing a limit, I bet we will get a limit at infinity equals to L. And that means just in case, this one is the standard one. This one we also have an intersection, okay, but just at infinity, we're respecting an asymptote. Okay, that's what is the point. Again, I will show you more complicated function. Most of them will be the rational function, and you have to know almost right away what is the limit at infinity, positive and negative, okay? And of course, remembering for the graphing part that this number, if it's finite number, is a horizontal asymptote. That means, let's see. Let's start with this one, because this will be our tool, yeah, like some basic things. That means if you will see a limit like this one at infinity or negative infinity, 1 over x to the power of r. But r is simply a positive number, okay? Because if r will be negative, everything will be flipped, and that will be not a case. This limit will be not 0. Okay, that means having like 1 over x, and x, of course, is infinity, it's a huge number, and even more because I will like put x to the power of 2, 3, 4, 5, always 0. That means this limit, as x goes to the infinity, let's say x to the power of 5. What is this limit? X to the power of 1 over x to the power, of course, 0. Okay, that means to any like, yes, any power. And I can do the same thing, even this one. Of course, is 1 over big number, but we don't distinguish the difference, positive 0, negative 0. The second one is approaching 0, probably from below, from the negative values, but it's still 0. And 0 will be a horizontal asymptote. That means one more time, 1 over big is simply small. Okay, it's remember. Of course, I can write this one for you. 1 over small is big, but that's different. Small is 0, big is infinity. It's of course really informal. Okay, that means let's remember this. 1 over big is small, and then let's look at more complicated problems. Okay. That's what I have. We will have few cases. Okay, let's look at the first one. That's what do you think? What is this limit? Limit at infinity, x approaches infinity, 1 over x minus 5. Of course, 0, right? Thank you, Pete. Because doesn't really, it's still 1 over big number minus 5, it's still big number. It doesn't really matter. That means you can, and I can tell you, like, of course, I'm not really, this is not like my normal residential class. That means I'm not looking at your work, which I wish to look like at like the steps that you're solving. But even if because I always ask students to provide the solutions, the steps for this type of question, no. If you know the answer, you know the answer, 0. But what I would like to show you, a little bit of algebra behind this, and then because it will be easier for the more complex problems. That's what I'm doing. I'm looking for the highest degree on the top and on the bottom. The top, I can't do anything, 1, I will leave it. But in the denominator, the highest degree, which is the degree of this function, is x, is 1. That's what I'm doing. I'm taking this x, let's look at this, and I did factor out. Right? If I will distribute this back, of course, x minus 5. Okay, and now, because what I'm trying to do, I'm trying to show you the tool that we just did. A number over big number will be always small. That's me. Let's see, 5 over x, 0. And then 1 over 1, and then 1 over x. And 1 over x is 0. Yeah? This is just it, just to show you a little bit of steps for a little bit of algebra behind this. But of course, it's 1 over big, it's simply 0. Okay, let's look at this one. Because this one is at infinity, limit at infinity, 2x minus 1 over 4x squared plus 5. That's me. What do you think? This one is a little bit infinity. Okay, that's me. First of all, I can tell you, we can complicate this a lot, because this theoretically, only theoretically, not practically, theoretically looks like a limit from calculus 2, which if you're gonna take the calculus 2 with me, 141, or with different instructor, you will probably see this type of limits. That's because what is this? If I do the direct substitution, I'm actually getting, where can I write? Infinity over infinity. And this is big thing. We call indeterminate form. We have 7 of indeterminate forms in mathematics, and this is one of them, and is one of the important one. That's we, and as we know, infinity is not a number, it's simply like indicating a big values, huge number. That is not the finite number. That's when I can't really cancel out and I say, oh, the limit is 1. No, I have to really investigate what kind of big numbers, what kind of infinity I have. Okay, that's me. Now let's see what we will do. I will do exactly the same steps to show you what is the answer that I did on the top line. That means in the denominator, I have 4x squared. I will leave it for x squared is the leading function. I will factor out, and on the top, in the numerator, I will factor out x. Okay, hopefully we're okay with this. Think always backwards, like x times 2, 2x. X times 1 over x, 1. X squared times 4, 4x squared. X squared times this fraction, x squared is gone, just 5. Okay, and now we can see the same thing. 1 over x, gone. 1 over big number, 0. 5 over big number, 0. Doesn't matter if it's any finite number on the top. And then I can okay, I'll show you the answer, but you probably see. Then I can simplify. This will be 1 over x. Okay, we have 2 and 4, that's finite, that's not important. But now I only have 1 over x. Everything else is like 0 or some extra like coefficients, 2 and 4. That's mean, but the main function is 1 over x. That means what will be this limit? Can you, it's now, yes, thank you everyone. It's 0, okay? That means it's definitely 0. Okay, let's do one more and I can tell you the pattern, which probably you figure out. Okay, what about this one? It's limited negative infinity. Okay, we have to be careful at some point, but it's just big numbers and negative direction. It's yes, yes, thank you, thank you. It's 0. Of course it's 0. Because what we have x cubed, okay, the leading function on the top, the leading function is x cubed. The leading function in the denominator is x to the power of 4. And if I will factor out everything else, this is, I can use red. This is 0, this is 0, this is 0, this is 0. Everything goes to 0, 5 and 1. But what's happened? X cubed and x to the power of 4. Again, 1 over x. Again, 0. Okay, that's me. Let's make the final conclusion. If I type this, if the degree, if we have rational function, of course, we're looking at the leading function, the degree of the polynomials from the denominator and from the denominator, numerator and denominator. If the denominator is winning in terms of the degree, always the limit will be 0, because we see the algebra behind. We will factor out everything else, doesn't matter, we'll go to 0. Only the leading function is taking a lead. I can say this way. Okay, that means if the degree of the numerator is less, or you can think denominator is winning, 1 over big number, because all of the numbers will disappear. We will get just a finite number. The limit is always 0. Okay, that's me now. What do you think? What is this limit? I'm not gonna factor out, and I'm not gonna, of course it's 0, because what is the battle? The battle is between x to the power of 5 and x to the power of 7. Denominator is winning always. Oh, I didn't type this, 0. And of course, just to have still the idea of the horizontal asymptote, for all of these functions, horizontal line 0 is a horizontal asymptote. Okay? Okay, let's do case 2. What about this one? Limit at infinity of 3x plus 5 over x minus 4. Yes, okay, okay. Ah, you know everything. That means now what we have, looking at the degree, actually the degree is the same. X to the power of 1 and x to the power of 1. But what I will do, I think I typed this, I will do the same thing. Okay, let's see, I will focus on my tool. I will factor out the leading functions, which is just x. This goes to 0, this goes to 0. And actually, I can cancel out, because they are identical function, x. And now, what is important? Important is the ratio of the leading coefficients. That means if the functions has the same degree, we're taking the ratio of the leading coefficients, because the function will go away. We can factor out them and cancel out, but the coefficients will stay. That means the answer is 3. Okay, get ready for the next one. What is the answer for number 6? 2 minus 3x squared over 5x squared plus 4x. Yes, yeah. Oh, no. Oh, I see some mistakes. I mean, I wanted to trick you. Yes, corrections. Oh, Kevin, correction. Yes, okay, I'm just looking. Okay. That's me. No, the answer is, okay, that's me. Now you can see, you don't have to really do all of this stuff. Now, you can, if the degree is the same, take the ratio of the leading coefficients. That means I saw the answer, I don't know even the name, because now the chat box says not 2 over 5. The leading coefficient is negative 4 and 5. Okay, I know that you know. Remember this, because for the multiple choice questions, no, you can't make mistakes. Okay, let's do numbers. Can you tell me number 7? Oh, number 7 is too easy. Yes, okay. I like number 6. Okay. That's me now. Of course, I did the math. You see how bad it looks like this. So, I mean, it's nice to see this, but the important thing is the ratio of the leading coefficients. Okay, that's my conclusion. If the degree is the same, take the ratio of the leading coefficients, because the function, like the same type of infinity is comparable. And now let's look at my question on the bottom. It's more like the exam type. Get ready, do not make the mistake. What is the limit of this function at infinity? Okay, yes, yes. Okay, I think the limit is 1. Really good. Because what I will do, limit, and I will just x to the power of 4, and I don't really have to know. And if I will distribute everything in the denominator, I also have my leading function, because as soon as it's the limit at infinity, we don't really care for the rest of the terms, theoretically. Okay, and it's exactly the same, it's 1. Okay, okay, that's in you, yes, you good. Okay, now let's look at the same case, but I will add one step more. I will add the radicals expression. Okay, that means, what do you think? What is this limit? Also nice exam type question. Quiz question. Limit at infinity, x plus 2 over square root of 9x squared plus 1. Okay, 0. But let's think. I know that it's not a typical rational function. It is the ratio. Okay, yes, yes. But it's okay. It's still we are on the learning mode. It's the ratio of two functions, and we have to we have to determine the degree. Degree on the top is obvious, x1, x to the power of 1. What is the degree of the function from the denominator? Who can tell me? It's also 1. Thank you, Jessie. It's also 1. Because I do have square root. Did I type the solution? Okay, I did type. Oh, okay. Because what I wanted to show you, I did the same thing, but let me do this. This is x, and I don't have to know the rest of them. And this is square root of 9x squared. Limit at infinity. Of course, I did the nice formal way. I did factor out everything, and this will be square root of 3. This is 1, and this is x and x. Okay, that's mean the same degree. But that's what I will do on this side. This is x, and this one is actually 3x, because square root of x squared, as x is positive infinity, is simply x. And then x is gone, 1/3 is the answer. Okay, that's how we can look. We can look at just this part. Okay, let's see another one. Limit at infinity, square root of 4x squared. Rest of them is not important. And in the denominator is 8x. That's mean, what is the answer? Okay, I see. Think about this. You have to simplify this, and you have to take 8x. Oh, I see some. What is square root of? Okay, I think the answer is 2/8, which is 1/4, which I see all of the answers 1/4. I did. Oh no, I didn't. I didn't actually type it. That's even better, because I will take this part and then like whatever left, which actually I can write a little bit like that. And then I can take 8x, factor out, and I don't even have to know what's happened. Okay, and then I have 2x over 8x, okay, which is 1/4. Limit as x goes to the infinity. Okay, that we have to look at this. But what is important, because so far what we did simplify something like that. Square root of x squared. And we're saying x. And this is perfectly fine if x is a positive number. Or in our case, if x goes to positive infinity. What's happened? How can I simplify this? As x goes to negative infinity. Okay, that means this is the thing, a little bit theoretical, but like you can imagine something like that. What is square root of I mean, Chris, did you type -1? But yeah, we have to add -1 to this. That's, I mean, we have to multiply by negative. That means the answer will be -x, which it's not really a negative number because x is negative and negative is positive. That means let's look at, yes, that's what probably you thought. Let's look at this one, like my x, now it's -5. I can't really say, I can't just copy, I can't just simplify this way. I can simplify the square root and square them. No, that's not true because -5 squared is 25. Root 25 is 5. That means what I can do, I can copy this number. That means I can copy, we can see that. Let me say, yeah, we can see that x is like -5. But what I have to do, I have to make it positive. That means adding additional negative in front, I am really making an expression, the final answer positive. That means please be really careful. If it's limit at infinity and you have to simplify the square root, always will be additional negative. Okay, I will erase this because I have next example, the same function like number 10, but at negative infinity. Okay, that means what will be this answer? It's the same thing. I have no problem. On the top is 8x, 8x. But in the numerator, I will have square root of 4, which is actually 2, and then square root of x squared. Okay, and this will be, yes, thank you, Kevin. Thank you, Chris. It's actually negative because this will give me -x. I still should put a limit. Okay, that's my, this one is simply -1/4. Okay, and this is the case that limits the positive 1/4 and negative 1/4 are two different asymptotes. One is at positive infinity, one is at negative infinity. Okay, but please remember, I did type for you, please make note for this simplification. We can't just focus on the first line. Oh, square root of x squared is x. Okay, it's x. It's x, but it's only if x is positive. Oh, hang on. We have one participant. I will stop the video. Hang on, and I will mute. Okay. Okay. Okay, that means please note about this and this because it's really easy to miss that. Okay. Of course, let's look at this the last line. The nice proper way to simplify this is the square root of x squared, value of x, and then we can deal with the definition of absolute value, which of course is positive or negative x, depends on the sign of inside quantity. Okay. Okay, that's me now. Let's look at the next case. Okay, I do have a list of lots of limits, but I don't want to go through all of them. Okay, let's see. Can you tell me number 12? I will just pick some of them, okay? Because we have to keep moving. Okay, who can tell me the answer for number 12? Is the limit at infinity, and then is the ratio of these two guys. Oh, somebody's typing 1/4. Oh, hang on. I have to. The fifth root, right? The fifth root of 32 is 2. Yes, and 2/8, because that's the ratio of the leading coefficients. It's 1/4. And for this one, like fifth root of x to the power of 5, we shouldn't be really worried. I mean, it's the odd root, but it's at positive infinity. Okay, can you tell me number 13? Cube limit at infinity, cube root of 8, x to the power of 6, and 4x squared. 2/4, 1/2. Thank you, Jessie. Thank you, Pete. Really good. Okay, and now where is the tricky one? Okay, can you tell me number 14? Limit as x goes to negative infinity, and it's square root of 16, x squared negative 2. Oh, Jessie, Kevin, Pete, and yes, I think it's, we will have -4 because it's from And it is -2. Thank you. Okay. That means you should be okay. Actually, one of them is tricky. Which one? Okay, because I still want you to really understand. Okay, let me do one more thing. Think about 16, but because what we did, square root of 16 is 4, and this is -x. Okay, and then of course we're not looking at the other terms, 2, -2. Okay, what about 16? Because 16 is something, yeah, okay, Chris, you typed, you typed -2 and +2, but I think the -2 is from the previous. Okay, square root of 16 is 4. 4 over 8, okay, 1/2. But now, okay, now Pete, you're asking if it's -1/2 or +1/2. Do you know what we can do? Also, one thing that we can be a little bit smarter. I mean, we always have to use the algebra and all of these rules, but let's really look at this function and think about the sign of this function at -infinity. Let's look at the denominator. I will take the negative numbers, big negative numbers, -infinity, and I will square this. X squared, that means negative number squared will be positive. That means my denominator is positive. And what about my numerator? X to the power of 4. Okay, that means I have no negative. Yes, thank you, Kevin. It's always positive. That means whatever we do, whatever number, of course we're gonna get the finite number, and we know that is 4 over 8. We know that is half, but definitely must be positive, because positive over positive will give me positive number. That means this is another way. But if we really would like to do the definition, I think this will be 4. This is still -x, but we will square that. Something like, that means actually everything will become positive. Okay? But this is more definition. Like you can always, for this type of limit, you can try to do the final check of your sign of the function at positive and negative infinity. Of course, positive is quite easy and quite like intuitive, but negative could be challenged. Okay, that's me. Yeah, I think rest of them should be okay. That's me. Now let's keep working on the next one. Okay, I do have few limits like that. They are, of course, a little bit different, but we still have to know like how the functions behave. That's what do you think? How function sine of x behaves at positive infinity? Because that's always like challenge, I think. That's what I always see. Is somebody answering? No? Okay, Pete is saying none. Yeah, that means how, yes, is really function sine of x like tending to approach one finite number? No. Oh, no, not 0, Kevin. No, I don't know. Yes, sine curve is simply, I should go through 0. Okay, pi, -pi, and so on. Okay, that we can see function is like oscillating between +1, -1, +1, -1. That means limit is undefined. Limit is simply, we can say limit does not exist as a one finite number. Okay, please remember sine of x, sine curve, cosine curve at infinity or negative infinity, they don't really exist as a finite number. Okay, that means this limit is undefined. What about limit sine of 1 over x? What do you think about this one? This one is 0, right? Because this one we can use the property, because since the function is continuous function, I can focus on my inner function first. And what is limit of 1 over x at infinity? Of course, is 0, and then sine at 0 is 0. That means this one is just, no, I'm not still. Okay, hang on, no, not this way. Okay, And I just realized we can maybe leave it number 20. It was in your textbook, but I think for me, looks more like a limit from Calculus 2, Math 141. Okay, because I definitely see some indeterminate forms, which we did infinity over infinity, but let's leave this one. Remember sign, okay? Okay, and now the final part of the limits at infinity are infinite limits at infinity, which means computing a behavior of the function at infinity at the endpoints. Function doesn't have any limitation, 0 or the finite number. Values of the functions are getting really big in the positive or negative direction. Okay, and then I do have few things which the same for this one. 24 looks like Math 141. Okay, x cube, how x cube behaves at infinity? Who can tell me this? Do you know how the graph of x cube looks like? You probably know. Oh, nobody's participating. Infinity, okay, hopefully you're not looking at the symbol, but I can simply say infinity. Algebraically, what this means, big number cube, of course, is huge number. Graphically, we do know a beautiful x cube. Okay, and function goes to positive infinity. At negative infinity, negative numbers, cube, of course, negative infinity. Okay, let's leave it 23 because it's also infinity and minus another infinity. A little bit too much. I don't know why the limits are in your textbook, but okay, let's leave it. We will definitely deal with the basic one. Okay, and 25, 26, and 27 are definitely the limits for us because that's what we were focusing. A rational function and the leading terms. I mean leading function on the top and on the bottom. That means the first one is limited infinity. And what we have 2x cubed over x squared. That means, what do you think? What will be the limit? Limit will be infinity because I didn't type, but we remember, if I will factor out, let me do this. If I will factor out the leading function without the coefficient, 2, and then I will have x over x cubed, 1 over x cubed. Then I'm factoring out the leading function from the denominator, 1 minus 10 over x squared. And we remember, this goes to 0, this goes to 0, this goes to 0. We know that. And what's happened? X cubed over x squared is simply x over 1, but it's x. That means we will end up having x in the numerator, big number, infinity. That means having only x, I can say x goes to the infinity. That means now you can probably see the conclusion will be, if the numerator is winning, always is infinity, positive or negative. Can you tell me number 26? Using, of course, the same. Okay, oh, we have to be careful. Positive infinity or negative infinity? Negative infinity, because I have this and this. After doing all of my steps, I will only end up with 4x. I can put my limit. Okay. Oh, actually negative, because that's my whole point. And then rest of the stuff are not. Algebraically, we know that they will go to 0. That means I end up with x, but x goes to negative infinity. We have to remember that. Okay, and the final one, 27. Limit at negative infinity. 1 minus x squared over 20x plus 3. Positive infinity or negative infinity? It's positive infinity, okay? Because we technically have this over this. That's my leading function, and this is my leading function. After simplifying, I will have negative x over 20. And x is negative infinity, then I will end up with positive infinity. Okay, and for all of these cases, coming back to our horizontal asymptote, no horizontal asymptote. Function is just approaching positive or negative infinity. Okay? Do you have any questions for this part? I will switch the light on. Let me just, because it's actually getting darker. Okay, I'm back. Oh, I think you can hear me now. Okay, no question. That's me. Let's see what we have. Okay, I have this question. This is, I would even say it's more just to finalize everything, the limits especially. It's more like algebra question, but let's just see if we can try to, what we have to do. We have to try to sketch the graph of the following function by finding its intercepts and its limit at infinity. Katin, what do you think? This is not really the rational function, but can you tell me how function will behave at positive or negative infinity? X goes to positive infinity, and how this function behaves. And negative. Okay, positive infinity, what do you think? Oh, Jesse, you just typed the answer because the last question was also, it's infinity. It's infinity. Because what we have, we can think that X is like a huge positive number. That means the first factor will give me positive number times another positive number and another positive number. Multiplying big numbers is still big number, positive infinity. And what about negative infinity? At negative infinity, it's still positive infinity because this will give me positive big number. This will give me negative, and I mean, let's do this. It's not really, infinity is not really a number. I can't really use in my algebraic like operations, but I'm just trying to test the sign because I know that it's huge numbers. But let's maybe even put, this will be negative number cube, and negative. That means negative number to the power of 4 is positive, negative number to the power of 3 is negative times negative, and negative times negative is positive because the other is positive. Okay, that means at positive and negative infinity, function is going up, positive infinity. Okay, can you tell me x-intercepts? And I can maybe draw it for you. What are the x-intercept? Yes, 2, -1, and 1. Really good. -1, 1, and 2. And now, what we supposed to do? We're supposed to like test the size of each. Hang on, before we do this, who can tell me the y-intercept? The y-intercept. I can of course help you, but I really want you to give me. We remember y-intercept means x is 0. Oh, 0, no. X is 0, 0, 0, 0. Who can do the arithmetic? No calculators, of course. No. Yes, Pete, thank you. Mean it's -16. That means somewhere, let's see, somewhere here. -16 is the y-intercept, really good. Okay, and function is going up, on the negative side. And hopefully we remember this because I don't want to really test everything. We do have the x-intercepts. We have to intersect them. But if we have them even multiple, which is like this one, x equals to 2, came like from the power of 4, we will not intersect the x-axis. Okay, I think we remember that. That means I will simply touch this. I can intersect one, and I should, hang on. Oh, okay, it's not, of course, I don't know exactly the height. I'm kind of guessing. And this one, let me come, at -1, since -1 is also a multiple, should be a little bit more flat. Okay, I don't have to put these arrows. but because we can see -1 came from the odd multiple, but which means always when we have higher power, the function becomes more like flatter at that point. Okay, but the most important part was the limit at infinity.